Record started.
We're good?
Yeah.
And I guess you're not directly recording the audio feed, right? So it actually doesn't matter if I'm speaking to the mic.
Doesn't matter.
Okay. Maybe I'll go without the mic. If anyone can't hear me, just say. I'll do something different.
Can hear you just fine, Gus.
Okay, great. So, hello, I'm Conrad. I just moved to Singapore in December and I got air conditioning in my living room last week. So now I'm really liking Singapore. I am a new assistant professor at NTU, and I also wear another hat, which is as one of the chairs of the WebAssembly community group. I'll talk a little bit more about that later, but the point is it's a standards organization for WebAssembly. So yeah, I'm going to be talking mainly about WebAssembly and JavaScript and the web. The connection to Rust is that a lot of people are now writing Rust programs that eventually get deployed as websites. And this is a very different experience sometimes from taking a Rust program and just compiling it to machine code and running it on the computer you control. Because the web as a platform has very different security constraints, very different sandboxing concerns, and often that means that when you try and take a program that thinks it's compiling to native assembly and compile it for the web instead, you give up some things, either in terms of performance or expressivity. And probably the biggest thing you have to give up right now is efficient concurrency. And so what this talk is going to be about is all the ways in which the web makes concurrency, especially shared memory concurrency, difficult, both in the context of JavaScript and WebAssembly. I'm going to be using C++ programs to explain why the compilation can get hairy, so apologies for that, but you can just pretend it's Rust, the same thing applies. And then I'm going to end up with a little bit of a talk about what the next steps are going to be to try and make the web better in this respect. Because it's certainly true that in the last few years, people have started to care a lot more about taking programs, putting them on the web, and still having them run efficiently, even if maybe they are creating a bunch of threads. So as I said, this is mainly a talk that's talking about problems and not solutions. I don't want to promise things that I can't unilaterally deliver, certainly to make the web better and to increase the capability of the web to do concurrency. It's going to involve a lot of powerful stakeholders agreeing to all go in the same direction, which is very difficult. It's very hard to get Microsoft, Google, and Mozilla and everyone around the table all agreeing on the same thing. But that's what we will need to do eventually to solve this problem. So for now, mainly going to be talking about the way things are and the reasons that's bad, and I'm going to very briefly hint at future directions, but no promises this is concretely coming. I don't have control over that. I can work towards it, I can try and get everyone on the same side, but I can't guarantee it. So I'll be talking about the capabilities and limitations of the web, as I said before, with a particular attention to WASM, because JavaScript is even worse. And yeah, very broad terms about future directions. I cannot guarantee anything. So how things are today. You may have seen a kind of mimetic idea that JavaScript is mostly single-threaded. And the first order exception to that is that in addition to running everything on the main thread, you can also create these web workers which run their own JavaScript scripts off to the side in a separate thread. For the purposes of this talk, I'm mostly going to be talking about workers and threads as synonymous. That's not necessarily true, but for the purposes of this, you can think when you create another worker in JavaScript, it's like you're putting it on another thread in the OS. Before I go any further, has anyone never touched JavaScript at all and is totally scared of all of this? Right. I think we're mostly good. This talk does assume some things, but if there's anything that's not totally clear, please just shout out at any point and I can clarify. But for our purposes, you can kind of think of workers as like a JavaScript thread. There's literally an instruction in JavaScript called create a new worker. You give it a script to run and it starts running that script off to the side, normally in a different OS thread. So one of the key kind of qualities of JavaScript that the whole language is designed around is that when you access a property in JavaScript, this actually involves quite a lot of work behind the scenes. There's almost nothing in JavaScript that corresponds to like a bare assembly load or a bare assembly store. You just don't have that available to you in the language. And the general feeling is that this semantics is so complicated that it's really hard to make it thread safe. So you kind of need to assume in JavaScript that everything just exists in one thread and never moves away from there and never gets access from a different thread. So concretely, what do I mean by that? Well, this is kind of the simplest thing you can write in JavaScript. You have like an object. Most things in JavaScript are objects. Every object in JavaScript is like a string dictionary. And you can access properties on the object. So this is like saying, go into object, which is my string dictionary, see if there's a string called foo, and if there is, take its value out and put that in variable x. So this is kind of one of the fundamental operations you would write down in JavaScript. Probably if anyone's written any JavaScript code at all, they've written a line like this. But actually, this line of code already, firstly, this isn't just a single assembly instruction to go into the object and just pull out the value. Firstly, as I was kind of alluding to earlier, it's actually a dictionary lookup, right? You can dynamically change the keys that are inside obj, and the property will dynamically look up, oh, is there currently a key defined for this particular string? Secondly, even if you don't find the string inside obj, there's this concept in JavaScript called the prototype chain, where even if you can't find foo inside this object, you then have to search through this kind of linked hierarchy of objects, which is kind of JavaScript's dynamic equivalent of a class hierarchy. And if you find foo in any of these, then you have to return that value. So actually, you're not just doing one dictionary lookup, you're potentially doing a linear number of dictionary lookups, depending on how long the prototype chain is. And even worse than that, you can actually make this line of code execute totally arbitrary user-defined JavaScript if you make foo something called an accessor property, which I'm not going to describe in detail, but just know in principle you can be executing an unbounded number of code, an unbounded amount of code as a result of just this line. You could literally make your own user-defined function, fill it with as much rubbish as you like, and stick it in there. And that will actually execute dynamically when this line of code is executed. So let's try and imagine this in a kind of a multi-threaded scenario, and this is where things break down. I maybe should have included one diagram before this. Just imagine this is a diagram first where all of these three things are within one worker. That kind of just about works, right? If this one worker contains all the objects, you're going to just be executing sequentially. Even if this line of code is really slow, you can do that lookup, you can do that arbitrary code execution, nothing gets complicated. Where things get much more complicated is if you try and have a situation where maybe you have one object here, but it's pointing to objects in another thread. And you can imagine maybe I created them all in one thread, and maybe I have some mechanism to shift an object over here. In C++ and Rust, you kind of don't really think about this, it's just slinging around references. You could very easily make this happen just by having like a shared global variable, right? We put objects in here and read it out here, and boom, it's in the other thread. Maybe in Rust you need to be a little bit careful about lifetimes and borrows, but you can still represent this, right? But within JavaScript, the problem is that as soon as I try to access this object in a worker, I'm going to try and follow references back to the other worker and do a lot of work under the scenes. So even though I'm just executing this line of code, suddenly I'm having to get my hands into the memory of other workers in order to complete the prototype chain lookup. And this gets complicated in particular for another quality of JavaScript, which is there's a very widespread assumption throughout the entire JavaScript ecosystem that basically is inherited from before workers even existed, that each individual environment, whether it's the main thread or a worker, can basically unilaterally decide to garbage collect things. And this makes sense from an efficiency point of view. If you didn't have this assumption, then if one worker has some things it wants to garbage collect, it has to stop all of the other workers before it can do any work. And that would be a regression in performance compared to the web as it is today. So this assumption has kind of persisted. But if we combine this hypothetical scenario with this assumption about how garbage collection works, you could have worker 2 suddenly deciding that it can garbage collect proto 1 because it doesn't see any objects that point to proto 1, right? It doesn't see this other worker's memory. So then it garbage collects proto 1, and then when worker 1 tries to execute this access, it follows the link and everything explodes. So clearly this isn't actually how the web works. But the thing that I've introduced in this hypothetical scenario that's not allowed in JavaScript is this concept of a reference between different workers. In real JavaScript, when you can have different workers, you just can't have references between them at all. They're kind of their own isolated worlds. They can do separate computation, they can communicate results by copying and message passing, but you can never hold references between different objects. And you can imagine that's a pretty severe restriction in comparison to the way native code works. It kind of just about works for JavaScript, because with JavaScript you're sitting down, you're writing your code specifically for the web environment. Where things get more painful is if you originally wrote your code in Rust, and then you try and compile it for the web environment, suddenly you have a mismatch of expectations. In Rust, you expect to be able to do this, if you have code that does this, what happens when it actually gets compiled to the web? Well, in the JavaScript case, everything kind of just falls over, and I'll describe WebAssembly in a little bit. But just to wrap up the kind of general zen of how JavaScript works, which is mainly something you approach and write yourself, JavaScript objects can only be accessed in the thread or the worker where they were created, and only referenced in the thread where they were created. And this is enforced at a very fundamental level of the language by the worker interface. There is actually just no primitive in JavaScript at all for sending a pointer of an object to another worker. You just can't express it. If you might think you're doing it, there's this message passing thing where you can send a message to another worker. But actually what that does behind the scenes is it makes a copy of the object. So you would never get a situation, where you create all of these three objects in one worker and then send the object to the other worker. Actually what would happen is those three objects would stay in worker 2, and worker 1 would get a copy of object 1 and actually a transitive copy of all the other thing it needs to make the references work. So this makes everything safe, but this is clearly a big limitation on expressivity, which just about works when you're writing JavaScript, but is a little more painful if you're writing another language that you want to deploy on the web. So the one exception to this is this concept called shared array buffer. And this is a relatively recently added feature to JavaScript that allows real concurrent access, as in it's really an object that multiple threads can reference at the same time. And the reason this is okay is because shared array buffer is not an object that can chain to other objects, like the arbitrary JavaScript dictionaries I described before. Instead, it's literally just an array of bytes and nothing else, so it can't hold a reference to anything else. I'll have a diagram for this in a second, but the point is that a shared array buffer, which is just this buffer of bytes, can't reference other objects, is the only thing in JavaScript that multiple workers can point to at the same time. So it kind of looks like this, right? You can have each worker, which will have its own object, which represents that worker's reference to the buffer. And then underneath there's a single buffer that both of them can touch. And this really means that if I write a value in worker 1 and read in worker 2, I actually get to see that happening with totally arbitrary concurrency. And this kind of gets you back to a C++ and Rust world, where you can just write these things as state and you don't necessarily even think about it. But reminder, this is disallowed. The only reason this is okay is because the buffer can't itself reference another object. You're not allowed any edges that look like this. So what would it take to do better than this and make even regular JavaScript objects concurrent? Well, this has been a long topic of discussion within the kind of industry body that's responsible for JavaScript. There was one kind of notorious previous attempt by WebKit, which is the Apple engine underlying Safari, which was essentially to do the brutal thing of just add a lock to every JavaScript object. So anytime you access any JavaScript object at all that might possibly be concurrent, just make sure you take a lock first. And I say seems too slow there. If you look at the blog post in detail, it was roughly 7 times slower. So obviously that was not going to fly. You can't just deploy this onto the web and have everyone's random script suddenly get 7 times slower because you put logs everywhere. So this approach, I think, is pretty much not going to work. We have some more ambitious ideas, which is some alternative mechanism for making a safe-to-share JavaScript object that can only point to other safe-to-share JavaScript objects. So now we have this kind of separate curated world of like more general objects, which we can't garbage collect in the same way, but that's okay because they're never going to point back into the regular JavaScript world. But as you can imagine, this is again itself like a restriction on expressivity, right? If you have your own existing code which just manipulates regular JavaScript objects, and suddenly you're told, migrate to this new world where you're creating a totally different kind of JavaScript object, and also if you try and kind of make the two worlds interact, you'll get an error. That seems like quite a bad developer experience. So there are some very, very early stage standards discussions about what it would look like to just concretely do this safe-to-share JavaScript object concept. And it really does seem like you have to move into a totally different world with some different syntax to possibly make it work. It's controversial. It's being pushed by a wonderful person called Shugo, who is now a Google engineer. Very serious concurrency guy, really knows his stuff. So if anyone can make this work, he can. But I should emphasize, this isn't a universally supported proposal. It's still going through the process of different stakeholders coming in, deciding what they think about it. And there are certainly negative voices. There are some people who get very scared of this idea of bifurcating the ecosystem. It seems a little unfriendly to developers. And even if we did have this new JavaScript object, we still need to convince every web engine, so that's kind of V8 in Chrome, SpiderMonkey in Mozilla, and WebKit in Safari, to extend their garbage collectors with this kind of new secret area of memory where all the shared objects live, safe from the regular objects. That's a very complicated engineering topic and probably one of the reasons there's not wider support for this proposal. So now we can move away from the decrepit world of JavaScript to the new and exciting world of WebAssembly. If a JavaScript standards person watches this video, I'm sorry. So the point of WebAssembly is, for years, if you wanted to build a website, you had to do it in JavaScript, right? And this in itself is also kind of a drag-on developer experience. Not everyone wants to write just JavaScript. Some people want to use their own language, and there are some tasks for which JavaScript is not ideal, such as doing very intensive computation. Remember how I said that even a property access in JavaScript, you never get down to an individual assembly instruction. Instead, you have this whole complicated game behind the scenes that the virtual machine has to do. So what that means is, maybe you want to do like physics simulation or 3D rendering or something in the browser, and if you have to code that in JavaScript, well, it can be hard to make that fast because you don't have tight control over what the machine is actually executing when it tries to run your JavaScript code. So WebAssembly has two purposes. Firstly, to support other languages for web development, in the sense that you write it in your favorite language and compile it to WebAssembly. People previously tried to do this with JavaScript. You may remember ASM.js or various other transpilers or things like that. Often they actually work quite well, but certainly there are some languages for which that's a little bit of a miserable experience, such as C++ and Rust. ASM.js was a great project. It got as far as it could, but when you're building on JavaScript, fundamentally there's only so far you can go. So it makes sense to try and have a new thing. And then the second motivation for WebAssembly is to get closer to bare metal performance. So if you write an instruction like i32.load, which is one of the WebAssembly bytecodes, you're pretty confident that that's getting relatively close to an individual assembly instruction, as opposed to maybe executing a big loop that has to run through all of your garbage collected memory, as has to happen in general in JavaScript. So what does WebAssembly currently have in terms of features? Well, as you can imagine, adding something as ambitious as WebAssembly to the web as just this totally new chunk that gets thrown into the web ecosystem needs to be done relatively carefully. And certainly the 1.0 release of WebAssembly, which happened roughly in kind of 2018 or so, was very conservative in terms of what it provided. We were very much focusing on supporting single-threaded C++ and Rust and basically nothing else. No Python, no JavaScript, no nothing. So very simple virtual machine model, which at a rough level of abstraction you can think of as being pretty similar to the JVM bytecode, except importantly no object type system. So if you look at the definition of the JVM bytecode, that actually has instructions like get field of object and things like that, which allow it to work with the Java memory model. WebAssembly didn't have anything like that baked in originally. Things are changing, but I won't describe that. Instead, you just had a linear memory, which is a simple buffer of bytes, and you should be twigging now this sounds kind of similar to shared array buffer, and there is a strong analogy which we'll get into in a second. So the idea is that if you have objects in your source language, well, if you compile those objects to JavaScript, you're kind of trying to turn them into JavaScript objects. That's why some people like to make a distinction between compiling and transpiling. But instead, when you're compiling to WebAssembly, it really is much more like a traditional compilation to platform assembly, where whatever the kind of structure of your objects in the source language, you're having to lay that structure out as raw bytes in the WebAssembly linear memory, and then trusting the compilation process to treat those bytes correctly to preserve the behavior of the object. So in terms of concurrent features, well, I already described how kind of the fundamental place everything lives in WebAssembly is this shared linear memory, which is just a byte buffer which matches shared array buffer. So we can make these shared. We can make WASM modules with shared memory. You can have that shared memory referenced by different workers at the same time. Actually, I realize I should have put this in a slightly different order, but by the end of this slide, everything will tie up together. So we have atomic operations like JavaScript, and we have wait and notify synchronization primitives like JavaScript. And all of these work off of our shared linear memories which work just like shared array buffer in JavaScript. So where WebAssembly still relies on JavaScript is that we have no native capability to create threads in WebAssembly. There's no thread create instruction. And this is actually quite a common thing with the way WebAssembly is set up. As I was saying, we were very conservative with our first release. So generally, the philosophy of WebAssembly is not that it's going to wholesale replace JavaScript in all contexts. We think it will replace JavaScript in some situations where you had to use JavaScript and you were unhappy about it. That's not every use case of JavaScript. Sometimes JavaScript is still the right thing for making kind of human-readable scripts for something you want to write directly. WebAssembly is not going to try and replicate every feature of JavaScript. And secondly, to be conservative with the release, we really did cut out everything from WebAssembly that could reasonably, uncontroversially be supported in JavaScript instead. So in particular, WebAssembly has this capability to, during points in its execution, say, I want to just jump out to JavaScript for a second and let JavaScript do something for me, and then I can continue execution afterwards. And one of the places where we built WebAssembly around this assumption was threads. So in WebAssembly, you never create a thread yourself. Instead, you do this thing where you're executing, you say, oh, I want to go out to JavaScript. JavaScript, please create a thread for me. And then once JavaScript is finished, you go back to WebAssembly again. And this is something that allowed us to keep the design of WebAssembly small, because it means you're deferring all of the complicated stuff, interacting with the wider web ecosystem and the web workers and so on. Just defer all of that to JavaScript, keep WebAssembly pretty lean. Maybe this isn't the most efficient solution for creating threads, but it was probably firstly the most politically feasible one to just get WebAssembly out into the world at all. And secondly, we can always try and do better in future and add native WebAssembly threads as a future feature. But this is the way things are today. So if you're on the web, you're basically calling out to JavaScript, asking JavaScript, please create a web worker for me so I can have multiple threads. Outside the web, probably the best thing you have right now is this plugin called WASI Threads. I don't know if anyone has played with this at all, but since this is a web-focused talk, I'm not going to describe it in detail, just to describe this is the kind of outside the web world, and that has its own complications. So now, our first kind of actual piece of source code, and it's C++, which I deeply apologize for, but you can basically pretend there's something analogous happening in Rust. So this is just a totally simple program which creates two threads and then waits for them to complete. And each of these two threads are going to increment both a thread local integer and a shared atomic integer. And the idea is once these two threads have executed, if I then check the values of these variables in the main thread, well, I can see the two increments for the shared integer, because both of those threads increment at the same location. But the thread local integer stays 0, because each thread gets its own copy of that, essentially. Is everyone familiar with this kind of setup for the difference between shared integers and thread local integers? I can go through it in more detail if anyone is not familiar with this setup.
Can you come again? What is basically 0?
So there are basically three threads here. There's the main thread, and there are the two kind of subordinate threads we're creating here, worker threads, each of which executes a copy of f. The difference between a thread local int and an atomic int is a thread local int, each thread gets its own copy of the integer that's totally separate. So even though a worker thread might increment its own copy of local int, that doesn't affect the local int that's in the main thread. The difference is if I declare something as an atomic int, there's just one copy of that all the threads see at once. So this is just the behavior of the different keywords. Atomic int means there's one copy that all the threads see. So if one thread modifies it, the other threads see that result. If it's thread local, each thread gets a separate copy. So even if I modify it in one of my worker threads, the main thread won't see that modification. So now the big, sorry, I'm like, oh, is there a mic coming? Microphone. Right here.
So is the local int here referring to the local int of the thread A or thread B? Since you say each thread is a...
Yeah, but there's implicitly a third thread, which is the original thread where you executed main. So you can think of there as being the main thread, thread A, and thread B. and this local int is the local int of the main thread, so neither of the increments show up. Does that make sense? Okay. So then we have to ask, well, how do we compile this to WebAssembly? So this is a syntax for WebAssembly, which is we call it a text format. You can kind of think of it as like JVM, like code mnemonics. Really, all of this is like a byte representation. These are just nice text keywords we use to refer to the encoding. So we have to, our local int, confusingly enough, becomes something called a WebAssembly global. I'll come back to that later. Put a pin in that point. The thread local int isn't actually that important for this example. So the important thing is that we have this shared memory that we're going to get from the environment. You're going to have the environment create a shared memory for you, maybe it's a shared array buffer. You're going to import it from the environment, and that's going to be the thing all of your objects get laid out in. You need to import a function from JavaScript, and I'm going to call it something like start new web worker, because you can't do that within WebAssembly yourself. And then I'm going to need to declare my own function called startup. This is basically just the body of the function that I'm eliding. But imagine there are lots of instructions in here, which is basically looking at the shared memory we imported and then finding a place for the shared int to be allocated there so all the different threads can see it. And then we have our compiled functions, which are the functions from the source program. That is our main function and our function f. The highlighting would have helped, but I forgot I had it. So the life cycle of a WebAssembly program this is a representation of the bytes of the module. The first thing you do in WebAssembly, in your main thread, which is actually going to start off in JavaScript, is within JavaScript you get the bytes of the WebAssembly module as an array. And then you call this function called instantiate. Well, let's say you call, how do I put this? Okay, let's stick with that. You call a function called instantiate. This is just part of the JavaScript API for dealing with WebAssembly. Take the bytes of a module, shove it into this function called instantiate, and the thing you get out is some compiled code from the bytes of the module. And also what you're getting out is this memory backing store. Actually, in this example, we allocated it separately. It could have been allocated with the module in certain circumstances, depending on the declarations. But for these purposes, just think of this as a JavaScript main thread. It's created the memory, which we're going to import, and it's created this compiled code of the module by calling instantiate on the original bytes of the WebAssembly module. And then the next thing you have to do is you have to create this thing called an instance. This is the final product of instantiation. So you've taken your WebAssembly code, within JavaScript you've called instantiate on it. You've created these things, and the final thing you get back is this instance. And what an instance is it's a JavaScript, this isn't totally correct, but for the purposes of this talk it's close enough. It's a JavaScript object, which is the JavaScript representation of the WebAssembly code. So this is actually an object that you will hold within JavaScript. It's basically a big bag of functions. And if you call one of those functions in JavaScript, you start executing WebAssembly. So just to go through the whole process again, this is an array of bytes. This is your JavaScript main thread. You're going to call instantiate on the array of bytes. You're going to allocate all this stuff, and at the end, you're going to get out an object in JavaScript with fields for all the functions you want to call and all the bits of WebAssembly state you want to access. So that's fine. Now we've got to the position where we can start executing WebAssembly. Within JavaScript, we can now call one of these functions and we'll start executing WebAssembly. But as soon as we do that, as soon as we start, I'm just removing all of the fields for space reasons, but they're still there. As soon as you start executing main of your instance that you just created, well, eventually, that's going to call start new web worker, right? Which is one of these JavaScript capabilities we called into WebAssembly. So that's fine. We go back to JavaScript, we create these new web workers, basically one for each of the threads we need. And each of these workers are also going to need their own copy of the instance. They can't share the original one. And the reason for that is basically what I've been setting up before in this talk, which is this is literally just a JavaScript object, right? It falls under all of the same restrictions as an ordinary JavaScript object, I can't take this object and pass it by reference into worker A. I can't take this object and pass it by reference into worker B, because that violates all of these assumptions about JavaScript you've been thinking about before. So actually what you have to do instead is create a copy of it in each of the workers you want to execute the code. And this is not very nice. As you can see from, I mean, maybe the lines make it look even worse than it actually is, but the point is, this is not an ideal situation, this is just what you need to do in WebAssembly to make multiple threads of execution work. You can't just compile your code once, get your bag of functions and start executing. Every time you create a new thread, you basically need to repeat this process to get a new copy of the code individually in each thread, so that you're able to actually fulfill JavaScript's restrictions on how objects work. And it's true, this memory backing store is like the shared array buffer, right? So you can see, this is just like my previous diagram where the shared array buffer can be pointed to by everything. This is the thing that makes the semantics work, right? All of your objects are going to be in here, even if there's a separate copy of the code. You do at least get to share the raw compiled code of the module. This is just one component of an instance. That's more about memory savings. From the JavaScript point of view, you still need to create this wrapper object around it that gets the point to the compiled code. So you could almost think of this as like a space-saving optimization. All of the difficulty of creating a copy is basically still there. And I'll just remove some of the arrows to make things a little neater. Does anyone have general questions about this setup? I can talk in more detail about this if kind of the abstract point I'm describing is not totally clear. But the high level point is, I'm now creating some new threads to basically make my C program run in WebAssembly in a way that's kind of conformant to the source semantics of the C program. Like we want this C program to behave like it would if you just compile it to assembly and drag it. But in order to achieve that, when I create my new threads, I need to create separate copies of the code, all pointing to the same memory backing store, in order that I can then have these workers execute their copy of function f, right, which is what was happening in the source semantics. Is that esoteric? Does it make sense to people? Yeah, so the thing I've been trying to set up is just, you should be familiar with the idea of needing to make a copy because I set up in JavaScript just for any kind of JavaScript object you need to do this. But what we clearly really want is we just want to, make this once, right? And then have all of the different workers pointing to it at once. And then things become very easy. You can almost, if I go back to my original C code, you really do just want one place that function f lives, right? And my other threads are going to take a reference to it, but it's not like they need to take a whole extra copy of function f in order to run, right? That's something we've had to introduce at the WebAssembly level in order to make the code behave like C. But at the C level, and if you compile the C straight to assembly, you're only going to have one place that function f lives, and all of the other threads are going to have a reference to it. So how do we get to this in WebAssembly? Which is going to, well actually there's one more kind of complaint I should make, which is this is really slow, right? So this process of starting a new web worker and then beginning to execute f in worker A and worker B, this is like not as fast as you would want it to be, because in addition to the overhead of creating a whole web worker, you're having to go through the process of compilation again, you're having to stitch up where the memory backing store is and all of the pointers. So what this means is, if you have a source program which is creating threads, you compile that to WebAssembly, suddenly it gets way slower, unless you play some very careful tricks. But that's because when you compile that C program to just assembly, when you create a thread, you don't need to make a new copy of all of the code in order to make it run, right? But in WebAssembly you do, because we're having to piggyback off of this JavaScript concept. This would make it faster, this would get us back closer to the where native code is. So we need to work out what it means to define a shareable WebAssembly instance. And there are some internal details of WebAssembly that also need to become more shareable as a result of this. But the main point is the instance needs to become shareable. And from our point of view, the main design pressure is the fact that we live on a JavaScript virtual machine. Pretty much every web implementation of WebAssembly is piggybacking off of a wider JavaScript virtual machine with all of the assumptions that come with JavaScript. And this was kind of a necessary compromise in order to get WebAssembly out of the door within 20 years. But it does mean that we now have these limitations. And the problem of making a WebAssembly instance shareable is basically the same as the problem of defining a safe-to-share JavaScript object, which is something I set up before. you kind of have the same possible directions of work and the same limitations. But maybe the necessary restrictions actually fit a bit better in WebAssembly. And I'm not going to go into more detail about this because I'd have to start kind of sketching things that may never exist. But the general point would be that, remember how I talked about in a safe to share JavaScript object, the first thing you kind of need to think about is you say, okay, well, we have a restriction that the safe to share JavaScript object can only point to other safe to share JavaScript objects, never back to regular JavaScript. So similarly, we'd have to have some kind of restriction that a shareable WebAssembly instance can only ever talk to other shareable WebAssembly instances, not kind of the existing non-shared WebAssembly instances. And that's a little miserable, but maybe it's more okay in WebAssembly because you're never writing WebAssembly directly. You write your source code and then you press a button and WebAssembly comes out. So if the compiler needs to do some work to match up, oh, make sure I'm only calling shareable things, you never see that, right? It's less okay in JavaScript potentially, because if there are mismatches between one object being shareable and one object being non-shareable, you as a developer directly suffer from that because you're trying to write the code that's in your head and it just doesn't work. But with WebAssembly, since you're just starting from the source language and pressing a button to get WebAssembly, maybe you don't need to see all the work behind the scenes that would need to happen to make all of the shareable restrictions work. And that might make it more okay, but no more details for now. So how do WebAssembly's current restrictions affect end users? Well, if you have concurrent code that wants to do a lot of manipulation in JavaScript, that can be pretty slow. So on the web, only the main thread is allowed to do this. This is actually something I maybe should have set up a bit better, but when you're creating these web workers, there are certain things they're not allowed to do. So if you have a source language where you just have some thread that says, oh, like paint a UI update or whatever, you need to do an inefficient workaround when compiling that to WebAssembly to kind of transfer that work back to the main thread and have it all go through. Not very fun. Also, concurrent code with dynamic code loading is torturously slow and probably unsupported in a lot of tool chains. One of the first places you'll see this is if you have a C program that calls dlopen, the system call. If you try and compile that to WASM, it'll either blow up or get disgustingly slow. And the reason for this is because in this scenario, we're kind of assuming that after we create the worker and make a copy of the code, you're kind of done and you can just start executing. But if you have dynamic code loading, which can bring in more code at arbitrary points in the runtime, the only way to keep this setup consistent is to pause everyone who has a copy of the code and update all of their code copies simultaneously and then start running again. So what that means is if you have dlopen, you compile it to WASM, you're basically putting a stop the world, stop the entire world, and rewrite every thread's code into your compiled code. It gets very slow. And also concurrent code plus runtime garbage collection deletes, or that should be slow, very slow. And this is a quality of, because everything in WebAssembly needs to be laid out in linear memory as bytes, that means your garbage collector needs to work over WebAssembly bytes. It now can't piggyback off of the JavaScript object model, some transpilers do. And when you have that plus concurrency, it's very hard to write a concurrent garbage collector without a lot of language support and a lot of special primitives, which WebAssembly currently doesn't provide. So in the absence of those, trying to combine these features together and compile it to WebAssembly is a miserable experience. So how do we move forward and get to a better world? So the JavaScript standard is governed by ECMA TC39, and for very boring copyright reasons, they have to internally refer to what they're working on as ECMAScript, but it's really JavaScript. And the WebAssembly standard is formally governed by the W3C WebAssembly Working Group, which in practice, we defer all of the decision-making to the WebAssembly Community Group, which I'm one of the chairs of. And the reason for this is, again, some very boring administrative stuff, where the thing that stamps the final edition of the spec needs to be called a working group, but if you want to participate in the working group, you need to pay a lot of money. So in order to make things more open, we make a second group that actually prepares the spec, passes it off to the working group who just stamps it, and that means that fewer people need to pay a lot of money to be involved with the specification process. So representatives from major tech companies participate in both of these groups and have very strong opinions about what decisions they should make, because obviously there are kind of millions to billions of dollars on the line, right? And at the very least, millions of dollars of engineering hours. if the standards body says, hey, JavaScript should have this cool new feature, you're basically committing everyone inside Chrome to spend all their engineering hours implementing that feature. And if it's kind of very complicated to implement, that makes Google sad. So the way you deal with this is Google shows up to the committee and kills the proposal dead before it can exist, because they feel it's infeasible to implement. I shouldn't have singled out Google there. Everyone does this. So you can kind of think the thing that finally gets through both of these committees is the lowest common denominator, where it's the thing that everyone's happy with, everyone's okay with implementing it. But that takes a lot of argument and a lot of time. Because clearly if you want a feature to kind of make the world better, suddenly you've got engineers from 4 other companies complaining about how much work it would be. And it can be hard to move things forward. It can take multiple years. So the upshot of this is there are many proposals and votes in our future in order to move towards a world where we have these kind of shareable WebAssembly instances and maybe native capability to create WebAssembly threads. It's something that a lot of people care about. We recognize that it would be very good for the ecosystem if these things existed. But there is quite rightly a very high political bar set on moving these proposals forward. One of the, I guess, the darkest moments of the earlier internet was when these standards bodies were much weaker and individual companies just did what they wanted, so you couldn't guarantee that if you made a website it would run on all web browsers, right? One of the advantages of having a more muscular standards body that people respect more is that you have this concept that the web isn't broken, right? If you write a web page, you can pretty much guarantee for the rest of time it's going to run in all browsers. Everything's going to be beautiful. But the cost of that is we have to be slower to add new features, because we have to make sure that the whole ecosystem is on board before we add them. And we're going to do our best, but this is why I'm being very careful not to promise anything, and mainly describing problems as they exist today. Because we're talking maybe 3 to 5 years of votes before the things I'm describing as potential solutions actually get into the hands of developers. So it's going to be a long game, essentially. But maybe you'll start to see some experiments within the next year or two. Okay. That's everything I have to talk about. I'm happy to take any questions about the content of the talk.
So in the original C++, there's an atomic int, right?
Let's have a look. Yes.
So does it become anything special when you become to WASM? Or?
So that's an interesting corner of the WebAssembly spec. It just becomes a regular cell in the memory, but what you do get is a guarantee that every time that cell is accessed, it's done using one of the atomic primitives in WASM as opposed to something less safe. So you can, I mean, yeah, that's a little bit, from my point of view, I'm used to the way WebAssembly does things, but essentially because this is an atomic int, when you increment it, it has an atomic behavior. The way that gets compiled to WebAssembly is this just becomes a regular location, but all of the places where an increment happens get promoted to being this magical new atomic operation instead of a non-atomic increment.
Is there any locking mechanism when the multiple threads in the shared or
Yes, so you can use wait and notify to implement locks. I didn't sketch exactly how it works. Where's the slide? This one. Yeah, so these wait and notify synchronization primitives, you can use them to build locks.
How much of that complication is applies on, let's say, non-web, right, where you control the runtime, let's say an app or a web worker or something, I think. Not web worker, but
yeah, you're
server
something like
backend
like a Node.js or something like that. Yeah. Is it? Am I?
Well, I'm actually thinking more like.
For like WASM time compiling to
That's
time.
more I'm thinking.
Yeah. So basically none of them. It's much easier.
Okay.
But the problem is, as I said, when we're dealing with a web standard, you get the lowest common denominator between all the stakeholders.
Okay.
So long as, so you're right that WebAssembly is kind of interesting because we have this large non-web faction who are using WebAssembly for a lot of server-side purposes, and this large web faction who are using WebAssembly for traditional web development purposes. And the way the standards process works is, yeah, you get the lowest common denominator between what's easy for them. So I'm describing why this is hard for the web, and that's unfortunately the reason that non-web needs to wait a little longer. If there was some kind of schism where we had separate standards for non-web WebAssembly and web WebAssembly, then you're right, the non-web people could move much faster with this.
I guess the previews are like that, right? Where they say, hey, here's something that's not agreed yet, but it might
Well,
be.
it's interesting because from this point of view, the previews actually still work within this model of being conservative with respect to the web. the way they get away with, so they're actually, how do I put this? So the concept of the previews is because they're imported functions, it's okay for them to exist only on the non-web and not on the web. What we're talking about here is a core language feature, so actually a new WebAssembly instruction. So it's much harder to add a core instruction that only exists on the non-web versus the web. I think the web people will be very upset about that because they own a lot of the tool chains like Binarian and so on. So if they feel pressure to implement an instruction that they don't support, it creates a political problem within the committee. So generally people are comfortable with the previews adding new imported functions which aren't widely supported, but the distinction there is it's not part of the core language, so we're kind of more okay with it.
I'll ask, where will we see like the web, multi-threaded WebAssembly in the web?
Multi-threaded WebAssembly. So you can see it today with these restrictions. That already exists because web workers already exist. Today, you can take your C++ code with pthreads, compile it to WebAssembly, and it will do this under the hood to make it work. So you can run it, you have to decide whether it's fast enough or not. There are certain ways of writing your code such that these overheads aren't actually so much of a big deal. And there are tricks you can do in the compilation scheme to reduce the burden of having to do this. So for a lot of code, it kind of just about works. In terms of when will we see this, 3 to 5 years of very lucky votes, or maybe never. That's why I'm not making any promises.
So this is not a current view.
This is where we want to get. This is what we want. And to get there, we'll need to add new features to WebAssembly along the lines of these safe-to-share JavaScript objects and shareable WebAssembly instances, which don't exist today.
So I just want to know fundamentally, what is the then current advantage with WebAssembly?
That it runs on the web at all, right? So if you think about, if you start from the process of, I want my app to run on the web, you basically have to choose either JavaScript or WebAssembly. At the very least, WebAssembly lets you write in another language and get it kind of somewhat working, right?
So you can point out C or C++ or Rust. So that's the advantage for WebAssembly.
Yeah, exactly.
Over the
Yeah,
JavaScript.
yeah. And to be clear, it's not perfect, but it's at least better than nothing, or at least better than compiling C to JavaScript, which is what people were having to do before.
So in that case, also we can achieve these references with the help of C++, right?
Yes. So if you take your C++ code, which creates threads, and run it through this existing tool called Emscripten, which is the C to WebAssembly compiler, behind the scenes, it will do all of this magic so that your C++ code that's creating threads in the source language will just work as you expect it to. But because behind the scenes it's having to do this work, it might be a little slower than you'd want.
Thank you.
But yeah, I guess from a negative point of view, you might say that the motto of WebAssembly is, well, at least you can run it on the web now. It doesn't always give you a perfect experience, but it's a very young technology. It already works in some scenarios, so may as well try it out, and we're continuing to work to improve it.
So what's your take on regarding blockchain with WebAssembly?
Blockchain and WASM.
Yeah.
It's a different use case, in the same way that you have the WASM-time kind of alliance of people who are very concerned with WebAssembly in cloud use cases, which is kind of separate from the web. Yes, you have a lot of people who are excited about WASM in blockchain spaces because they see it as this nice universal format with few copyrights and a good tool chain and so on. I mean, you laugh, but that's an important point. Imagine trying to put the JVM on the blockchain, right? Would you want, like, I don't know, another lawsuit? So it's validating, I think, for us to see WebAssembly having success in all of these different use cases because it shows us we just designed a good virtual machine. I think it is interesting that we mostly haven't seen blockchain people then come back to the standards and say we want this new extension to WebAssembly to be added. Well, interpretation for that is that we're already good enough, we're doing everything right for them, they don't need any more. which might be true just because I think it turns out that smart contracts tend to be a little bit simpler. Because they need determinism, they generally don't have threads, so they don't have any of these problems. They generally don't care about the minutiae of like floating point or vector instructions. You just want a fairly simple bit of code executing. So it might be that WASM as it exists today is already totally sufficient for all of these smart contract use cases, which is good. There are some spaces that are trying to use WASM and it doesn't work very well for other reasons, like in embedded systems with very low resources. There may be some intersection with blockchain there, maybe if you want to run a bunch of nodes but you don't have much memory to provision to them or something like that. And in these low resource environments, one of the difficulties with WebAssembly is that the default smallest size we specify within WebAssembly for the memory backing store is 64 kilobytes. So if you want to use a device with less than 64 kilobytes of memory somewhere internally, often WebAssembly isn't a good fit, and we're actually discussing, we discussed yesterday, a potential proposal to allow a smaller memory backing store to make WebAssembly work better on embedded systems. But I think that the motto is, we've been surprised by how many different places WebAssembly has become useful. As I said earlier, that makes us feel like we just designed something good, and lots of people find that it fits their use case. One of the things we need to be a little careful of is, as I said, in the standards body, we have to take the lowest common denominator between all the different competing interests. So the more different interests there are in WASM, in some sense, the slower WebAssembly moves, which I think is just an inevitable quality of trying to keep one definition of WebAssembly across all of these different ecosystems. Definitely a trade-off, but the advantage is you just have one tool chain which you can kind of just maintain and everyone gets to use it. So Binarium, which is this WebAssembly optimizer, it turns out basically everyone can use it in all of these different use cases because WebAssembly is just this one universal definition that stays the same. And if we did have this bifurcation or this schism where different WebAssemblies were defined for different environments, we would lose a lot of that nice property. So there are advantages and disadvantages.
You have 4 more minutes.
I don't have anything more to say, but I'm happy to take more questions.
Any questions? If not, then we'll move to the next speaker.